Thanks for joining us today for this webinar on noise, vibration, and harshness for magnetic-induced noise in electric machines. My name is Paul Larson, and I am a magnetics engineer with a specialty in multiphysics applications, including electric machines and noise. I would also like to mention the Ansys Learning Hub. So before I describe that, I'll say that last year we held a series of workshops on multiphysics NVH for electric machines, and that was received with a lot of interest. And so this material, including training and tutorials, has now been transferred and hosted on our Ansys Learning Hub website. So you can access these training and tutorial workshop materials on demand, as well as other Ansys electric machine simulation training materials. So this includes a variety of topics for electric machine modeling and design, including the magnetics, thermal modeling, structural, and acoustics. So this is all hosted on the Ansys Learning Hub, which you can find out more information and inquire with your Ansys team how to get access to these materials. So with all of that intro, today I will be talking about electric machines and the process from electric to magnetic to structural to sound for the simulation of magnetic-induced noise. And this can be applied to other applications as well, but electric machines are certainly a hot topic here. So what I'll be presenting today is a variety of topics, and I'll introduce the workflow for NVH simulation, and then describe a series of updates to our different simulation tools and our workflow that allow for highly efficient simulation. So these updates really highlight the benefits of simulation and accessibility of our built-in connections between these Ansys tools. And these allow engineers to really understand the noise impact of their design decisions. And then finally, I'll walk through an example to highlight the benefits of these updates and how that fits into the total processes here. So let me get a pointer up. Okay. So NVH is one aspect of many multiphysics challenges for high-performance electric machines. Within the larger Ansys portfolio, we consider all these multiphysics challenges to aid machine designers. The first to mention, of course, is to understand the thermal performance of the machine in order to avoid damage in the windings and magnets, and the effect of these temperature dependencies on the machine performance. The topic of today's webinar, of course, is understanding acoustic noise, and we will dive deep into this workflow. Of course, within the realm of electric machines, this has become more important as electric machines replace components that often make much of the noise and with a much different noise signature, especially when we're talking about replacing combustion engines or reducing the amount of gearing or transmissions required in different assemblies. So the majority of your noise might be produced by this electric machine with its signature electric whine instead of the broadband noise sources of the past. And so it's a different challenge for acoustic noise in electric machines. And these first 2 points really lead into these subsequent topics in terms of discussing the mechanical implications of these vibrations, the implications of both vibrations and thermal stress on lifetime, as well as understanding and avoiding and suppressing mechanical resonances. So in all of these mechanical structural studies, the structural modes and damping need to be well understood, as well as the fixturing and bolting and how these need to support the entire life cycle of this multiphysics electric machine. And these are all challenges that Ansys helps our customers address through simulation. So that's the high-level view. At Ansys, we approach this holistically with a suite of multiphysics tools that can be deployed against all these challenges, either together or one at a time. So in today's presentation, we will focus on the workflow here for magnetic induced noise, which can be represented in a lot of different ways. But we'll start with this workflow chart, where starting on the left-hand side, we have the magnetic simulation to calculate the forces within an electric machine. And this will produce these force waveforms that are based on the magnetic analysis, including motion and external drive circuits. So all the complications of a magnetic simulation produce forces, and those forces are then used in a dynamic structural model to look at the vibrations and forced response of the electric machine and fixturing. Then this structural vibration response is used as an acoustic source for radiated acoustic noise. And then the many different physical sources of vibration and acoustical noise are all combined, whether from fans, gearbox, road noise. They're all added together within the structural chassis by including propagation and transfer paths, and then how this leads to airborne sound and perception that the driver would be experiencing. So this whole process provides a complete simulation workflow for the sound simulation of a real car or within a driving simulator. So the engineer and designer can hear the noise before they go out and work on prototypes. The way that we support this workflow is within the Ansys workbench to transfer and link together multiple models. So workbench is a multi-physics tool, a connection tool to link together these different physics solutions, and it provides methods to transfer the geometry from one type of physics to another, as well as transferring fields and forces between different solvers, even as this points out with dissimilar mesh, and like we see in this example here, could be with dissimilar a 2D magnetic simulation connected to a 3D structural, or it could be 3D to 3D as well. So it's a very flexible tool that allows a lot of efficiencies in the simulation process and allows other things like design variation and parameters. The simulation challenge is how we bring all these components together efficiently to simulate and accurately predict these noise sources. So, of course, as I mentioned, there are many different contributions to noise sources, whether it's electromagnetic, mechanical, like gearboxes, or airflow, aeroacoustic noises like wind noise or road noise coming from the tires. So all these different sources could certainly be brought together within our tools. Today, I'm focusing mostly on the electromagnetic forces which are produced by the forces within the air gap of the electric machine. So as the electric machine produces currents on each of these forces acting on each of these teeth to commutate and electrically rotate the rotor, then that produces vibrations and forces back on the motor. So the key goal of our simulation is this flexible, efficient, and accurate way of combining all these different sources. And I think that's what I'll be able to point out to you in an environment that we can evaluate the desired outputs efficiently and bring it all together to perform optimizations and improve the sound and performance. On the structural side, this requires modal analysis, harmonic response, fatigue. It can include a lot of different elements of this structural analysis. The workflow that I'll show both requires and provides insight into the structural response of the electric machine and the fixtures. And so this is integrated within the workflow. So we can start with a modal analysis to really understand the response of the fixturing and the housing. And then we also use that to efficiently produce the acoustic results. So the other points about bringing up fatigue is that acoustic noise is often a symptom of vibration processes that can lead to fatigue failures. So we can link the harmonic vibration response, the force response, to a fatigue analysis and see what that cycling will do. Once we have the structural response that's well understood, then it's a fast process to obtain a full waterfall diagram, for example, representing the multi-speed response of the machine. So we'll dig into the waterfall diagram in a few slides here. But our workflow provides methods of looking at multi-RPM magnetic models, producing forces for all these speeds, and then evaluating the structural and acoustic response. So that's the high-level overview, and we'll dig into how we do that. In our workbench environment, this is built up with these blocks. We have geometry blocks and our magnetic Maxwell blocks. And the solutions for the forces on our magnetic blocks are connected directly. Their forces are transferred to the forced harmonic analysis. And we see other blocks here that represent the sequence of the structural analysis. So we can have a preload on our modal analysis. So this can be pre-stressed to get different vibration response. The modal analysis allows us to get very efficient speed and frequency sweeps for the harmonic response, as well as providing a lot of insight into the types of interactions that we need to either avoid or suppress with damping and other methods. And then we can either use the harmonic response solutions directly or connect that into the acoustics module, which will provide sound pressure level as well as acoustic propagation. So This waterfall diagram keeps showing up, and it's one of the key takeaways of this workflow for multi-RPM models. So let's dig into it a little bit and describe how it provides a full acoustic fingerprint for this machine. So we'll take a look at a couple different lines here. So first we have this vertical line that's circled here. And this provides one frequency. So if we had a microphone that is filtered to a single frequency and we sweep the speeds, we would be able to just focus in on what that frequency looks like versus speed. Okay, so that's one representation of just slicing this model, this result plot. So let's look at this horizontal line. This horizontal line would represent just running the machine at one speed and then seeing the spectrum of frequencies that are produced by the noise. And so this would just be holding the speed at a fixed value and doing a Fourier transform of the noise waveform. Would give you this type of spectrum. These inclined lines that end up having a lot of the noise peaks represent different orders of the noise. And so these orders have particular meaning for both the mechanical engineers who might talk about the orders of the rotation, orders of this the fundamental rotation speed. And they also have particular meaning to the electrical engineers who might talk about the synchronous speed and the fundamental frequencies associated with the synchronous speed as well as the harmonics. So we do see a lot of information represented by some of the resonances that might show up on specific frequencies. They could be structural in nature. It could be caused by switching in the PWM drive. Or it could just be that there are strong orders that interact with the structure. So there's a lot of information represented by this one diagram. And we'll keep showing it for different cases. So I wanted to walk through that. So now let's talk about some updates that can bring about some efficiencies for modeling in electric machines. And the first update is for the 2D multi-slice model. And we've had this 2D multi-slice model for skew available in Maxwell for several versions. And we are making connections to this harmonic force calculation for NVH. And when this skew model is enabled and we calculate harmonic forces in Maxwell, then we will automatically generate these harmonic forces for each slice of the skewed model. So then those forces will be transferred to the full 3D mechanical model. So this is an example here. We would set up the skew model in Maxwell, assign the properties, and then once the harmonic force is enabled, it will be calculated for each slice, each layer of the skewed model, and transferred appropriately to the full 3D skew model in mechanical. Another thing that we're providing inside of Maxwell is some further reports for the frequency domain forces that are calculated inside of Maxwell. So in the last several versions, we've added different capabilities for object force transfer, surface force density transfer, and volume force density transfer. So all of these provide a lot of different options, different capabilities for modeling, I'd say, more complicated scenarios. But we're adding these post-processing options in Maxwell so that you can really interrogate and see what those force results look like without having to map those into mechanical. So, of course, the mapping is done automatically, but now we're getting a little more insight into what those frequency domain force densities look like. Some other updates that I can really describe really help the efficiency of the solutions that we're going to look at, of course. So any type of speed ups will include the improve efficiency in our multiphysics modeling. And we've had a lot of really good speed ups over the last several versions. So what's pictured on this slide is some of our TDM capabilities, including the periodic TDM and half periodic TDM, which are really, really good for synchronous generators, including damper bars, including PM machines with induced currents. We can get some really, really good speed ups by taking advantage of more cores. And so this is really powerful, really beneficial for multiphysics modeling. The other thing that's really interesting is using Ansys in the cloud. And we have built-in methods to launch the simulation software in the cloud, and it will solve and simulate and then send back the results to your machine. And there are a lot of ways that this can be used for magnetic machine design of electric machines, as well as pre-solving Maxwell models that could be used for further multiphysics analyses. So the cloud is not yet fully set up for all the multiphysics connections yet, but we can definitely pre-solve the Maxwell model in the cloud and then import all those solutions into any type of workbench multiphysics analysis. So this can be combined with a lot of our HPC type of analyses to really give a good speed up. So in this case, maybe your local machine only has 8 or even 16 cores, and it's taking you 4 hours or more to do a large 3D problem. We could definitely speed that up on the cloud and get you results over a lunch break. So in addition to these magnetic speedups, magnetic updates, we have a lot of specific workflow enhancements, and especially for the speed sweeps. And speed sweeps are necessary for these waterfall diagrams and a lot of other different cases that we'd want to see. So what we do with the speed sweeps is when we read in the load information. So load here is when we transfer data from one solver to another. And when we read that in, we automatically read in all of the information that's transferred, that gets mapped from one solver to the other. And we also synchronize the analysis settings. So it will read in the speed and the number of frequencies, the frequency range for each speed, so that it's ready to solve. And you can always go in and adjust the solution settings. So you could do a subset of the frequencies if that's what you want. But by default, it's reading in analysis settings from the prior solutions, from the mapped workflow solutions, so that it's ready to go. And this really automates the process. It makes it a lot more accessible, a lot more relatable, and lets you see what the sequence of events needs to be. Another really, really powerful update a couple versions ago is this built-in calculation for equivalent radiated power and equivalent radiated power level. And what I really want to point out with this is that it gives a really fast estimate of the total radiated acoustic power that's based on the structural vibration. And so we can get a sort of signature of, if we get this machine and we install it in some open environment, how much total noise power is it going to radiate? So we can get some idea of maybe even the worst case or the average case radiated noise. And this allows us to very quickly try to optimize the design to reduce that total noise. And so I bring this up here because it's so easy to implement, it's so fast to calculate, and it produces very nice waterfall plots. So it's a really nice workflow feature that both mechanical and electrical engineers can understand and very quickly get to some way to design and simulate the acoustic performance of their machines. Of course, you can always go to the next level and do that acoustic analysis to get sound pressure levels and to get interaction and scattering of the environment. But this definitely produces a very efficient simulation. Then one other simulation update that just came out recently, or is coming out very soon, is the RPM speed interpolation. And this is just one more case that we are making to improve the efficiency of calculating these forces very, very efficiently so that we can calculate the sound. And this allows us to enter a setting in the force transfer setup that will let us solve just 2 points. And so, for example, in the constant torque region that we show here, maybe our current angle are identical across this whole range. And so the forces that we're going to experience here are going to be almost identical across this whole range. And we don't want to have to solve at all these different speeds to produce this waterfall plot. But if I only choose a couple, then we're trying to very loosely interpolate between. So this setting here lets us shift the frequencies, interpolate the frequencies between these 2 points, and provides a much more uniform efficiency or waterfall plot here. And so you can see the effect of not just solving at 2 points, but solving at 2 points and interpolating at 4 points in between. And so everything else is done automatically by the software. We just enter the number of points here and then resync the analysis settings, and it automatically has all this information to solve and produce results.